well, sorry. I really don't mind if you're walking a little bit late. I know that you guys come from other buildings and some professors give you overtime. So as long as you quietly enter the room, I have no problem with walking in a little bit late. Would anybody want to start the attendance sheet? Or who wants to be the one? Roberto, please. Thank you so much. All right. We're walking through the chapter 12 a little bit fast, and I would like to start with a review of 12.1, 12.2, 12.3. So two things we will do today. Part 1 will be review of chapter 12, sections 12.1, 12.3 from the book, and starting chapter 12, section 12.4 today, later. What is that about? This is about surface integral, surface area, and all right, what have you seen in 12.1, 12.3? Let's review quickly what you've learned. You've learned about how to interpret an integral of a positive function that is smooth, well, we said continuous, that would be enough, over a rectangular region, and the geometric meaning of such a problem, integrate f of x, y positive over a domain, was what? The volume of the body under the graph and above that domain. So projecting it down on the domain. Evaluate that body. How did we do it? Double integral of f of x, y, dx, dy, or dA. But then we said, okay, if you have a rectangular region on the ground, then it's easy. You apply the Fubini theorem, and then you have integral from a to b, integral from c to d, fixed endpoints. When you didn't have a rectangular region to integrate over, you would have such type 1, type 2 regions who were easy to deal with, which were the case of regions like the ones between two straight lines and two functions, and then you had the type 2, two straight lines and two functions, where the functions were assumed differentiable, actually, in our examples. Type 1, type 2, what did we do after that? After that, we said, well, what if you're not so lucky and have such nice domains, or maybe you have something with a corner? What do you do if you have a corner? Well, you'd still be able to divide the surface into two, or you have two separate areas, and then you integrate on them separately of the same type, and you have an additive integral. The integral will be additive. Those are easy to deal with. But what if you've had something that is more sophisticated, like a disk or an annulus? And in that case, it's really a big headache considering how to do this using one of the previous types. So we had to introduce polar coordinates, and we had to think, what change do I have from x, y to r theta polar coordinates back and forth? And when we did the double integral over a domain f of x, y function positive dA in Cartesian coordinates, when we switched to polar coordinates, we had a magic thing happen, which was what? Some f of x of r theta, y of r theta. I say theta, I put phi. It doesn't matter. Let me put theta if you prefer theta. A change of coordinates, a Jacobian, that was what? Do you guys remember that? R, very good, I'm proud of you, R, and then the R, the theta. So you're ready to do that kind of homework, integrals, double integrals in polar coordinates. The R will be between hopefully fixed values, because that will make the Fubini-Tonelli piece of cake. Theta, also fixed values, but not always will you have fixed values, especially in the first part. You may have some function of r, and here theta 1 and theta 2. So I want to see a few more examples before I move on to section 12.4, because as the Romans said, review is the mother of studying, which is repetitio est mater studiorum, which means go ahead and do a lot of review if you really want to master the concepts. Okay, I'm gonna take the plunge and go ahead and help you with your homework. I've been pondering about this a lot. We've done problems that I made up, like the ones in the book, and I also took problems straight out of the book. But I would like to go over some homework type problems in order to assist you in more easily doing your homework. In chapter 12, homework 4, am I right? Homework number 4, you have a big array of problems, all sorts of problems, because mathematicians have all sorts of problems. For example, an easy one that you're not going to have a problem with, and I'm using my own endpoints, your endpoints may be different in the homework, would be homework 4, chapter 12, number 4, and you say, most of you should say, oh, that's a piece of cake. I don't know why she even talks about such a trivial problem, right? Many of you will say that. Well, I am willing to review everything so that you have a better grasp of the material. On this one, since it's so easy, I want you to help me. What kind of problem is that? As I said, mathematicians have all sorts of problems, right? So a problem where you have a product inside as an integrand, where the variables are completely separated. What does it mean? The function underneath is a product of two functions. One function of x only, the other function of y only. Which is a blessing in disguise. Why is that a blessing? I told you last time that you can go ahead and write this as a product of integrals. Is there anybody seeing already what those integrals will be? Let's see how much you mastered the material.
X from 2 to 1.
From 1 to 2 you said?
Yeah, from 1 to 2, sorry.
So there will be
Oh, what?
X.
X dx times integral from 0 to pi of what?
Cosine 1.
Cosine y. Do we need to reprove this result? No, we proved it last time. But practically, if you forget, the idea is a very simple thing. When you integrate with respect to y, Mr. X said, I'm not married to y, I'm out of here, I'm out of the picture, I'm going for a walk. So integral of cosine is in itself to be treated first independently, and it's inside, and it's a constant, and it pulls out in the end. And since it pulls out, what you're going to be left with afterwards will be that integral of 1 to 2x dx. So we've done that last time as well, yes sir.
So you would you not be able to do that if it was like cosine xy?
Absolutely. If you had cosine xy, it's bye-bye.
So it's only when
If-
they're completely separate. And just
When
multiply
you're
them.
lucky enough to have a function of x only times a function of y only.
All right.
And if you had another result, cosine of x plus y, anything that mixes them up, that would be a bad thing. Do I have to compute this? Not if I'm smart. At the blink of an eye, I can sense that maybe I should do this one first. Why? Integral of cosine is sine, and sine is 0 at both 0 and pi. So it's a piece of pie. So I have 0, and the answer is 0. So you say, okay, give us something like that on the meter because this problem is a piece of cake. Yeah, I can do that. Probably you will have something like that on the midterm on the April 2nd midterm. So So, since Alex just entered, I'm not going to erase this for a while until you are able to copy it. I announced starting the surface area integral today, section 12.4. We'll do that later on. And I will move on to another example right now. Oh, now they learned. Look, they learned about me. They learned about me that I have lots of needs, and I don't complain, but they noticed that these were disappearing really fast. Everybody else told me that I write a lot on the board compared to other professors. I don't know if that is true, but I really need this big bottle. Okay. So you've actually solved this by yourselves. You just don't realize I'm not going to take any credit for that. And I'm going to go ahead and give you something more challenging. See if you are ready for the review and for the midterm. Okay, that's number 9 on your homework. That may have again the data changed, but it's the same type of problem. Now you cannot ask me about number 9 anymore directly from web work, because I'll say I did that in class, and then if you have difficulty with it, that means you did not cover the notes. This is pretty. You've seen that one before, and I would suspect that you're not going to even let me talk, because look at it. Evaluate the following integral. And it doesn't matter what numbers we are going to put on that and what funny polynomial I'm going to put here. You are going to have all sorts of numbers. Maybe these are not the most inspired ones, but this is web work. It creates problems at random, and every student may have a different problem. That is in order to minimize cheating, and that's okay. The type of the problem is that matters. So if we were in Calc 1 right now, and somebody would say, go ahead and take it integral of e to the x squared dx and compute it by hand, see what you get. You already know. They don't know, poor people. They don't know, but you know, because I told you that this is a headache. You need another way out. You cannot do that in Calc 2. And you cannot do that in an elementary way, by hand. This is something that MATLAB would solve numerically for you in no time if you gave certain values and so on. But to find an explicit form of that antiderivative would be a hassle. The same thing would happen if I had a minus here. In that case, I wouldn't be able to express the antiderivative as an elementary function at all. Okay, so this is giving me a big headache. I'm going to make a face, and I'll say, oh my God, I get a headache. Unless you help me get out of trouble, I cannot solve that. MATLAB can do that for me. A Maple, I can go in and plug in the endpoints and hope and pray that I'm going to get the best numerical approximation for the answer. But what if I want a precise answer? Not a numerical answer. Then I better put my own processor to work and not rely on MATLAB or Maple. Okay. Understandable, precise answer. Can I leave it unsimplified? Hopefully, yes. We need to think of what technique in this case? Change the order of integration. Okay, all right. And in that case, the integrand stays the same. These two guys are swapped. And the endpoints are changing completely because I will have to switch from one domain to the other domain. The domain that's given here by this problem is the following. X is between 7y and 7. and y is between 0 and 1. So do they give you horizontal strip or vertical strip domain? Horizontal. Very good. I wasn't sure if I heard it right, but anyway. What is this function and that function? So x equals 7 would be what? X equals 7 would be far away. I have to do 1, 2, 3, 4, well, 5, 6, 7. This is a vertical line, x equals 7. That's the x-axis. That's the y-axis. I'm trying to draw the domain. And what is x equals 7y? X equals 7y is the same as y equals 1 over 7x. That should be a friendlier function to draw, because I'm smart enough to even imagine what it looks like. It has y equals mx is a line that passes through the origin. It's part of a pencil of planes. A pencil of planes is infinitely many pencil of lines. I'm sorry. Infinitely many lines that all pass through the same point. So they all pass through the origin. For 7, x equals 7 is going to give me y1. Y equals 1. So I'm going to erase this dotted line and draw the line. This is y equals x over 7. And we look at it and we're very happy. Look how nice it is and how ugly it is, because it's fat. It's not a straight line. And now it looks straighter. So simply I get to 1, y equals 1 here, which is good for me because that's exactly what I wanted. I wanted to draw the horizontal strips for y between 0 and 1. I know I'm going very slow, but that's kind of the idea, because do you mind that I'm going so slow? Okay, this is review for the midterm, slowly a little bit. So y between 0 and 1, I'm drawing the horizontal strips, and this is exactly what you guys have. This is the red domain, let's call it D. It's the same domain, but with horizontal strips. And I'm going to draw the same domain. What color do you like? I like green because it's in contrast with red. I'm going to use green to draw the vertical strip domain and say, all right, now I know what I'm supposed to say. That D with vertical strips is going to be x between, yes, first the fixed numbers, 0 and 7, and y between
0
and
1.
This one. X over 7, 1 over 7 is. Right? Is it x over 7? X over 7, y equals x is the same thing as y equals x over 7. So y equals x over 7 is this fellow, which was the same as x equals 7y before. Okay, so how do I set up the new integral? I'm going to say dy dx, and then y will be between 0 and x over 7, and x will be between 0 and 7. Is it solved? No, but I promise from my heart that if you do that on the midterm, you get 75% on this problem. Even if it doesn't say don't compute it. If it says don't compute it, leave it like that, you got 100%. Okay? So this is the most important step. From this on, I know you can do it with what you've learned in Calc 1 and 2. It's a piece of cake, and you should do it with no problem. Now, how are we going to handle this fellow? This fellow says, I have nothing to do with you, Mr. Y. I'm out, and you're alone. I don't need you as my friend. I'm out, I'm independent. So Mr. Y starts sulking and say, I have integral of 1 dy between 0 and x over 7. I'm x over 7. So you are reduced to a very simple integral. That is the integral that you learned in Was it Calc 1? Calc 1, yes, the end of Calc 1. All right, so you don't need the picture anymore. You've done most of the work, and you say, I have integral from 0 to 7 x over. So this guy, which one shall I put first? It doesn't matter. E to the x squared got out first. So I'm out. And then integral of 1 dy was y between these two, so it's x over 7 dx. And this is the 7. All right, we are happy. So what happens? 1 over 7 also goes for a walk. And x dx says, okay, I need to think who I am. I have to find my own identity because I don't know who I am anymore. So he says, I need a u substitution. U substitution is u equals x squared, du equals 2x dx. So x dx says, I know at least that I am a differential form, a one form, which is du over 2. And that's exactly what you guys need to change the inputs. 1 over 7 was a constant, he got out of here, but you have to think, when x is 0, what is u? 0. When x is 7, what is u? 49. Even my son would know this. Well, he would know more. He would know fractions and stuff. Okay, so e to the u, and the 1 over 7 was out, but what is x dx? Du over 2. So I'll say 1/2 du. Are you guys with? Could you follow everything? Yes, shouldn't be a problem. Now, 1 over 7 got out, 1 over 2 get out, everybody gets out. And the guy in the middle who is left alone, integral from e to the u du, what is he? E to the u. Between what values? Between 49 and 0. So I'm gonna, shall I write it again? I'm too lazy for that. E to the u, okay, I'll write it. E to the u between 49 and 0. So I have 1 over 14 parentheses e to the 49 minus e to the 0, that's a piece of cake, 1. Okay, so presumably if you answer that in web work, this is the precise answer. If I did it correctly, you would get the right answer. Of course, you could do that with the calculator. MATLAB could do it for you, Maple could do it for you, Mathematica could do it for you, but they will come up with a numerical answer and approximation, and you haven't learned anything in the process. Somebody just served you the answer on a plate, and that's not the idea. Is this hard? I'm saying on a midterm that's based on the double integral with switching order of integrals, this is as hard as it can get. Cannot get anything worse than that. So that will tell you about the level of the midterm that's coming up on the 2nd of April. Not something to be worried about. Do you need to learn a little bit during the spring break? Maybe a few hours, but I would not worry my family about it and say, there is this witch, and I'm going back to heaven, and I have to take her stinking midterm, and that stresses me out, so I cannot enjoy my spring break. By all means, enjoy your spring break, and just devote a few hours to your homework, but don't fret, don't be worried about the upcoming exam, because you will be prepared. And I'm going to do more reviews so that you feel confident about it. Another one, well, they're all easy, but I just want to help you to the best of my extent. One more. They're also easy, okay, let's take this one because it's not computational and I love it. It's number 14. Number 14, number 15 are so much the same type, and 16. It's a theoretical problem. It practically tests if you understood the idea. That's why I love this problem. And it appeared obsessively, this problem, I saw it in, I've been here for 14 years. I've seen it at least on 10 different finals. The same type of theoretical problem. So it's number 14 over homework 4. Find an equivalent integral with the order of integration reversed. So you need to reverse some integral. And since you were so savvy about reversing the order of integral, you should not have a problem with it. And WebWork is asking you to fill in the following expressions. You know the type. F of y, you have to type in your answer, and g of y, you have to type in your answer. Okay, so you're thinking, I know how to do this problem. It must be the same idea as before. This integral should be, according to the order of integration, should be vertical strip thing, switching to horizontal strip thing. And once I draw the domain, I'm going to know everything. And the answer is yes, you can do this problem in about 25 seconds. The moment you've learned it and understood it, it's going to go very smooth. And to convince you, I'm just going to go ahead and say 0 and 1 and draw, Magdalena. You know how to draw. Come on. Okay, from 1, 1, 1, right? Is this the corner of a, does it look like a square? Yes. So the parabola y equals x squared is the bottom one. Am I right that it's the bottom one, guys? Between, you see, when you are between 0 and 1, x squared is a lot less than square root of x. Square root of x is the top. Is the function on top. And then you say, okay, somebody gave me the vertical strips. I'll put dot in it, but I don't need them. I'll just go ahead and take the purple and I'll draw the horizontal strips. And you're already there because I see the light in your eyes. So tell me what you have. Y between 0 and 1, excellent. And y between what and x? Oh, sorry guys. I need to rotate my head, right? That's the secret recipe. X is between a function of y. What's the highest function of y that can be?
Square root of y.
Square root of y. And who is that fellow? This one. X equals square root of y, the green fellow. I should have written in green, but I was too lazy. And this one is going to be just x equals y squared. So between y squared down, who is down? F is down, right guys? The bottom one is F, which is the bottom one is y squared. The upper one is square root of y. Oh, you cannot type that in WebWork, right? You type SQRT, what? Y caret 2. And here, what do you have? 0 and 1. So I talk too much, but if you were on your own doing this in WebWork, it would take you no more than, I don't know, 60 seconds to type in. Remember this program for the midterm. It's an important idea, and you've seen it emphasized. You will see it emphasized in problems 14, 15, 16. It's embedded in this type of change the order of integration type of problem. Okay? Anything else I would like to show you from? There are many things I'd like to show you, but I better let you a little bit do things on your own. How about 17, which is a similar type of problem, theoretical, just like this one, but it's testing if you know if you understood the idea behind polar integration in polar coordinates. Can I erase? So let's switch to number 17 from your homework. Write down the problems we are going over. So when you do your homework, you refer to your lecture notes. This is not a lecture. It's what is this? What you're doing now? It's like a what is this? Application session, a problem session. Okay. Number 17. Homework 4. On this one, unfortunately, I'm doing just your homework because there is no data. So when there are, it's the unique problem you're going to get. You have a picture, and that picture looks like that. From the airplane, a half of an annulus. You have a half of a ring, and it says, suppose that R is the shaded region in the figure. As an iterated integral in polar coordinates, the double integral over R, f of x, y, dA, is integral from A to B, of integral from C to D, of f of r theta times r dr d theta with the following limits of integration. A, and Weber says, you say it. You see, it's playing games with you. B, you say it, it's a guessing game. C, you say it, then D, you say it. And let's see what you say. Well, you say, well, how am I going to go? Let me see. I have to disclose the graphing paper. They are so mean. They don't show you the actual numbers. They only give you graphing paper. Well, I'm not good at graphing, okay? So you'll have to guess what this says. No, that should be good enough for everyone. So the unit supposedly is this much. 1 inch, whatever. Okay. So, is it hard? It's a piece of cake. It's a 10-second problem. It's a good problem for the midterm because it's fast. Theta is a wonderful angle. He's nice to you. And they really don't put numbers here. They do on the margin of the graphing paper, they have like a scale. Okay. So, come on, this is easy. You guys are too smart for this problem. From what to what? No, that's the problem. So, when we measure the angle theta, where do we start measuring? Over here. So we go counterclockwise, because that's how we mix in the bowl, counterclockwise. So 0, pi, ooh, sharks. So this is going to be pi. And what is the end? 2 pi. 2 pi. Don't type both. I mean, you cannot type the symbol pi, right? And then what do you type in terms of C and D?
Minus.
No, the radius is positive always.
0 to 1.
1 to 2. Why 1 to 2? Excellent, because the shaded area represents the half of a donut. You have nothing inside. There is a hole in the donut. So between 0 and 1 you have nothing, and the radius, take a point in your domain, is here. The radius you have, the red radius you guys see on the picture, is a value that's between 1 and 2. Between 1 and 2. And that's it. That was a 10-second problem. So promise me, you are going to do the homework and stuff. You have 2 or 3 like that. If you see this on the midterm, are you going to remember the procedure, the idea of the problem? Okay. I'm gonna also think of writing a sample. I promised Casey I'm gonna do that, and I did not forget. It's gonna happen after spring break. You're gonna get a review sheet for the midterm. I promised you a sample, right? Okay. Shall I do more or not? Yes? You know what I'm afraid of really? I think you will be able to do fine with most of the problems you have here. I'm more worried about geometric representations in 3D of conics, that the quadrics that you guys became familiar with only now, only this semester, and you have a grasp of them, you've seen them, but you're still not very friendly with them, and you don't quite like to draw. So let's see if we can learn how to draw one of them together and see if it's a big deal or not. Because it's pretty as a picture. But when we set it up as an integral, it should be done wisely. Shouldn't be hard. We have to do a good job from the moment we draw. And if we don't do that, we don't have much chance. Problem is going to change the data a little bit to numbers that I like. 29. You have a solid, and I say solid gold, 24K, I don't know what. That is between two paraboloids, and those paraboloids are given, and I'd like you to tell me what they look like. One paraboloid is y, no, sorry. Yeah, one paraboloid is y, I'll change it, z, so I can change your problem, and then you will figure it out by yourself. Z equals x squared plus y squared. They give you y equals x squared plus z squared, so you have to change completely the configuration of your frame. And then z equals 8 minus x squared minus y squared. I'm changing problem 29, but it's practically the same. Find the volume of the solid enclosed by the two paraboloids and write down the answer. Find the volume of the solid enclosed by the two paraboloids. Oh, you go, oh my God, how am I going to do that?
Draw the picture.
Draw the pictures, very good. So he's teaching my sensing to me and says, okay, go ahead and draw the picture, don't be lazy, because if you don't, it's never going to happen. You're never going to see the domain if you don't draw the pictures. So the first one will be the shell of the egg. Easter is coming, so let's do something like the shell. It's a parabolic shell, paraboloid, circular paraboloid. And that is called z equals x squared plus y squared. Okay. This guy keeps going. But there will be another paraboloid that has the shape of exactly the same thing upside down. Where is 8? 8 is far away.
It's on.
I'll try.
Did they tell you that A had to be positive?
Huh?
Did they tell you A had to be positive?
Which 8?
That A. Or whatever.
8.
Oh, 8.
8.
Oh,
So
that's why
how
I'm
do I know
confused.
it's 8? Because when I put x equals y equals 0, I get z equals 8 for this paraboloid. This is the red paraboloid. The problem, my question is, okay, it is like two eggshells that are connecting exactly the Easter egg, but the how do you call that? Boundary, the thing where they glue it together. What is the equation of this circle? This is the question. Where do they intersect? How do you find out where two surfaces intersect?
They said the same.
Solve a system. Make a system of two equations and solve the system. You have to intersect them. So whoever x, y, z will be, they have to satisfy both equations. Oh my God, so we have to look for the solutions of both equations at the same time. Which means that I'm going to say these are equal, right? Let's write that down. X squared plus y squared equals 8 minus x squared minus y squared. And z is whatever. What is this equation? We'll find out who z is in a second. Z has to be x squared plus y squared. If we find out who the sum of the squares will be, we'll find out the altitude z. Z equals what number? This is the whole idea. So x squared, I move everything to the left hand side. So I have 2x squared plus 2y squared equals 8. And then I have z equals x squared plus y squared. And then that's if and only if x squared plus y squared equals 4. So z equals 4. So z equals 4 is exactly what I guessed, because come on, the two eggshells have to be equal. So this should be in the middle of between 0 and 8, right? So I knew it was z equals 4. But I had to check it mathematically. So z equals 4 and x squared plus y squared equals 4 is the boundary. Let's make it purple because it's the same as the purple equation there. So the domain has to be the projection of this purple. It looks like a sci-fi thing. You have some hologram, I don't know what it is. It's all in your imagination. You want to know the domain D. Could somebody tell me what the domain D will be? Will be those x and y's on the floor with the quality that x squared plus y squared will be between 0 and 4. So I can do everything in polar coordinates. This is the same thing as saying rho theta, r theta, not rho. Rho is Greek. It's all Greek to me. So rho is sometimes used by people for the polar coordinates, rho and theta, but we use r. R squared between 0 and 4, you'll say, Magdalena, come on, that's silly. Why didn't you write r between 0 and 2? I will. This is 2, right? So r between 0 and 2. I erase this. And theta is between 0 and 2 pi. And I'm done. Why 0 and 2 pi? Because we have the whole egg. I mean, I could cut the egg in half and say 0 to pi or something. Invent a different problem, but for the time being, I'm rotating a full rotation of 2 pi to create the egg all around. So finally, what is the volume of, suppose this is like in the story with the golden eggs. They are solid gold eggs. Wouldn't that be wonderful? We want to know the volume of this golden egg. What's inside the solid egg, not the shell, not just the shell made of gold. The whole thing is made of gold. And who's coming tomorrow to the, sorry guys, mathematicians, okay, switching from another. Who's coming tomorrow to the Honor Society? Did you decide? You have. And Rachel comes. Are you coming? No, okay. Tomorrow night. Tomorrow, what time did I say? At 3 o'clock. At 3 o'clock. Okay, so if you want, I can pay your membership and then you'll be members. I saw one of the certificates. It was really beautiful. The one last year was really some parents frame these things. My parents don't care, but I wish they cared. So the more certificates you get, and the older you get, the nicer it is to put them, to frame them and put them on the wall of fame of the family. This certificate, the KME one, looks so much better than my own diplomas, the PhD diplomas and math diplomas. And it's huge, and it has like a gold and silver seal, metallic stuff, and it's really nice. Okay, now coming back to this thing.
Can we multiply by 2? Like, just find the bottom?
Exactly, that's what we will do. We could set up the integral from whatever it is, one function to another function. But the simplest way to compute the volume would be to say 2 times and set up the integral for this one, for example, right? Or the other one. It doesn't matter which one. Doesn't really matter which one. Which one do you prefer? I don't know. Maybe you like the bottom part of the egg more. I don't know. Do you guys understand what I'm talking about?
If we did
So-
the bottom one, would it find the area, the area left, like that's indented, or would it? Because I'm like, if you did it from the bottom, like the domain is 0, and you have, wouldn't it find the stuff that was like not cupped out, sort of like the edges?
Isn't it exactly the same volume up and down?
Yes.
It's the same volume up and down, so it's enough for me to take the volume of the lower part and double it.
Okay.
Can you help me set up the lower part? So I'm going to have 2 times. Can I do that directly in polar coordinates? That's the thing. 1 is 1. R is R. R is going to be, this is the Jacobian, R d theta. Okay? But now, let me ask you, how do we compute, I'm sorry, this is the function f of xy. Yeah, it's a little bit more complicated. So you have to subtract from one the other one. So I'm referring to the domain as being only the planar domain. And I have first a graph and then another graph. So when I want to compute, forget about this part. I want to compute the volume of this, the volume of this egg inside. I have to say, okay, integral over the d of the function that's on top. The function that's on top is the z equals f of xy. And the function that's on the bottom for this egg is just this. So this is just a flat altitude g of xy equals, what is that, 4. So I have to subtract the 2 because I have first this body. If this would not exist, how would I get the purple part? I would say for the function f, the projection on the ground, I have this whole body that looks like a crayon. Okay? Whole body that looks like crayon. This is the first integral. And minus the cylinder that's dotted with floating points, which is this part. So is V1 minus V2. V1 is the volume of the whole body that looks like a crayon. V2 is just the volume of the cylinder under the plane. V1 minus V2 is exactly half of the egg. Half of the egg, the volume of the half of the egg. Okie-dokie. So, is this hard? It shouldn't be hard. F of xy, can you guys tell me who that is? A minus x squared minus y squared. And who is G? 4. Just the altitude, 4. Okay, so I'm going to go ahead and say, okay, I have to integrate 2, double integral over d. 8 minus 4 is 4, minus x squared minus y squared, dA. dA is the area element dx dy. Now, switch to polar. How do you switch to polar? You can also set this up as a triple integral. That's what I wanted to do at first, but then I realized that you don't know triple integrals, so I set it up as a double integral. For a triple integral, you have 3 snakes, and you integrate the element 1, and that's going to be the volume. And I'll teach you in the next 2 sessions. 2 times double integral. Who is this nice fellow? Look how nice and sassy he is. 4 minus r squared. Times, never forget the r dr d theta. Theta goes between 0 and 2 pi, and r between 0 and 2. Excellent, because when I had 4 here, that's the radius squared. So r is 2. Look at this integral. Is it hard? Nah, not so hard. Not so hard at all. So what would you do if you were me? Would you do a u substitution? Do you need a u substitution? This is silly. You don't need it. So just say 4r minus r cubed. Now what do you see again? Theta is missing from the picture. Theta says, I'm out of here, I don't care. So you get 2 times integral from 0 to 2 pi of nothing, well, of 1 d theta, not of nothing, times integral from 0 to 2 of 4r minus r cubed dr. For r minus r cubed dr. Integral from 0 to 2. Good. Who's going to help me? I give you how much money? Time shall I give you to do this one? And I need 3 people to respond and get the same answer. So what do you do? R squared, 2r squared minus r to the 4 over 4 between 0 and 2. Can you do it, please?
4.
How much did you get?
4.
How much did you get?
For just this one?
For all this.
4. Nope.
Yes, it is, right? Are you with me? You have 2r squared when you integrate minus r to the 4 over 4 between 0 and 2. That means 2 times 4 minus 16 over 4. 8 minus 4 is 4. So it's 4 for this guy, 2 pi for this guy, and a 2 outside. You have 16 pi. And that was, I remember as if it was yesterday, that was on a final 2 or 3 years ago. Okay. So you've seen plenty of these problems now. It shouldn't be complicated to start your homework. Go ahead, if you want, go ahead and start with the problems that we did today, and when you see numbers changed or something, go ahead and work the problem the same way, make sure you understood it. I'm going to do more. Is this useful for you? I mean, okay, so you agree that every now and then we do homework in the classroom? Yes. Okay. Homework-like problems in the classroom. In the homework, you may have different data, but it's the same type of problem. Okay. I'm going to remind you of some Calc 2 notions, because today I will cover the surface area.
Dr. Luna, I have a
Yes, sir.
question about last
Yes,
problem.
yes, sir.
If we had seen something like that on the exam and had done it using the fact that it's a solid revolution,
Yeah, you can do that. There are at least 4 methods to do this problem. One would be with triple integral. One would be with double integral of function on top minus the function below. One would be with solid of revolution, like in Calc 2, where your axis is the z-axis. I don't care how you solve a problem. Again, if I were the CEO of a company or the boss of a firm or something, I would care my employees to be solving problems the fastest possible way, as long as the answer is correct. I don't care how you do it.
thank you.
So, go ahead. All right. Oh, and by the way, I want to give you another example where the students were able to very beautifully cheat and get the right answer. That was funny. But that is, again, Calc 3 problem in the elementary way that can be solved with the notions you have from K-12, if you master them really well. So you are given x plus y plus z equals 1. Before I do the surface integral, I could do the surface integral for such a problem. This is a plane that intersects the coordinate planes and forms a tetrahedron with them. Find the volume of that tetrahedron. Now I say with Calc 3, because the course coordinator several years ago did not specify with what you learned, set up a double integral or set up, he simply said find the volume. So the students, what's the simplest way to do it?
Let's just have you.
Just draw the thingy. And they were smart, they knew how to draw it, they knew what the vertices were. The plane looks like this. If you shade it, you see it, it's x plus y plus z. And I'm going to try and draw it with my hands. It's very hard, but it comes from like 0, 0, 1 point. This is the 0, 0, 1. And it comes like that. And it hits the floor over here. And these points are 1, 0, 0, 0, 1, 0, and 0, 0, 1, the vertices of the tetrahedron, including the origin. How do I know those are exactly the vertices of the tetrahedron? Because they verify x plus y plus z equals 1. As long as the point verifies the equation, it is in the plane. For example, another point that's not in the picture would be 1/3 plus 1/3 plus 1/3, 1/3, 1/3, 1/3. Anything that verifies the equation is in the plane. So the tetrahedron has a name. It's called, let's call this ABC and O. OABC. It's a tetrahedron, it's a pyramid. So how does the smart student who was not given a specific method to solve that, they did that on the final. I was so proud of them. I said, come on, the final is 2 hours and a half. You don't know what to do first. So they said, take the area of the base, multiply by the height, divide by 3. So you get 1 times 1, yeah, so practically divided by 2, 1/2. You don't even have to do the area of the, even my son would know that this is a half of a square, 1 by 1 square, so it's a half the area of the base. Times the height, which is 1, divided by 3 is 1/6. And goodbye and see you later. But if you wanted, if the author of the problem would indicate, do that with calculus 3, then that's another story. Because you have to realize what the domain will be, the planar domain. You practically have a surface. The green shaded equilateral triangle is your surface, which let's call it CS from surface, but this would be Z equals f of xy. How do you get to that? You get it from here. Explicit equation is, pull the Z out, 1 minus x minus y. That is the surface, the green surface. And the domain, let's draw that in. Do you prefer red or purple? You don't care? Okay, I'll take red. 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 That's the domain D. So you'll have to set up I, integral, I for an I, volume, double integral over E of f of xy, whatever that is, dA. That's gonna be, who is D? Somebody help me, okay? That's not easy. So to draw the domain D, I have to have a little bit of a skill. If I don't have any skill, I don't belong in this class. What do I have to draw? Guys, tell me what to do. 0, x and y. To draw z0, z equals 0 gives me x plus y equals 1, right? So this is the floor, guys. This is the floor. So why don't I shade it? Because I'm not sure which one I want. Do I want vertical strips or horizontal strips? You're the boss, you tell me what I want. So, do you want vertical strips? Let's draw vertical strips. So how do I represent this domain from the vertical strips? X is between 0 and 1. These are fixed variable values of x between fixed values 0 and 1, right? For any such blue choice of a point, I have a strip, a vertical strip that goes from y equals 0 down to 1 minus x up. Excellent, excellent. This is exactly, Roberto, you are the one who said it. Okay, so this is the domain. So how do we write it down? 0 to 1, 0 to 1 minus x. That is what I want to write. No polar coordinates. Goodbye, there is no problem. This is all typical Cartesian problem. F is 1 minus x minus y. Thank you very much. This is F. dy dx. Homework gets 1/6. So try to do that at home. And get a 1/6. And of course in the exam, in the exam you would cheat big time, right? What would you do? You would set it up and forget about computing it, integrating one at a time, right? Doing this. And you would put equals 1/6. Thank you very much, right? Can I check that you didn't do the work? No! You trapped me, you got me. I have no, I need to say, is this correct? Yes. Is the answer correct? Yes. Do they get full credit? Yes. So, it's a sneaky problem. Okay. Now finally let's plunge into 12.4, which is, can you remember this problem? For 12.4 I want to draw this again, so I'll try not to erase the picture. I'll erase all the data I have here, and I'll keep the picture because I don't want to draw it again. When we were small in Calc 1 and 2, they gave us a function y equals f of x. That is smooth, at least C infinity, C1. C1 means differentiable, and the derivative is continuous. And they said, okay, between x equals a and x equals b, I want you, any student, to compute the length of the arc. Length of the arc. And how did we do that in Calc 2? I have colleagues who drive me crazy by refusing to teach that in Calc 2. Well, I disagree. Of course, I can teach it only in Calc 3, and I can do it with parametrization, which we did, and then come back to the case you have y equals f of x and get the formula. But it should be taught at both levels in both courses. So when you have a general parametrization, r of t equals x of t, y of t inflate. This is a parametrized curve that's C1 in time. What is the length of the arc between time t0 and time t1, guys? Integral from t0 to t1 of the speed, because the space is integral of speed in time. Okay? So instead, in terms of speed, remember that we put square root of x prime of t squared plus y prime of t squared dt. Why is that? Somebody tell me. That was the speed. That was the magnitude of the velocity vector. And we've done that, and we discovered that in Calculus 3. In Calculus 2, they taught this for what case? The case when x is t, say it again, Magdalena, the case when x is t and y is f of t, which is f of x. And in that case, as I told you before, the length will be like integral from a to b, whatever, it is the same thing, a to b, square root of, since x is t, x prime of t is 1. So you get 1 plus y is just f, y is f. So you have f prime of x squared dx. So the length of this arc, let me draw the arc in green, it's beautiful. The length of this green arc will be length of arc. Integral from a to b, square root of 1 plus f prime of x squared dx. Now there is a beautiful, beautiful generalization of that for generalization or extension gives you the surface area for a graph of a graph z equals f of x y over domain D. Say what? Okay, it's exactly the same formula generalized, and I'd like you to guess it. So I'd like you to experimentally get to the formula. It can be proved. It can be proved by taking the equivalence of some sort of Riemann summation and passing to the limit and get the formula, but I'd like you to imagine you have. So you have a z equals f of xy that projects exactly over D. The surface of this, the area of the surface, let's call it A of S. The area of the surface will be, what do you think will be? You are smart people. Will be double integral instead of one integral. Over what do you think? Over the domain. Yep. What's the simplest way to generalize this bubbly, ugly guys? Another square root. We don't have just one derivative, f prime of x. We are going to have two derivatives, f sub x and f sub y. So what do you think the simplest generalization will look like?
1 plus x.
1 plus f sub x squared plus f sub y squared dA. That's it. So you say, oh, I'm a genius, I discovered. Yes, you are. I mean, in the sense that, no. In the sense that we all have that kind of mathematical intuition, creativity, that you come up with something. And you say, okay, can I verify, can I prove it? Yes. Can you discover things on your own? Yes, you can. Actually, that's how all the mathematical minds came. They came up with a conjecture based on some prior experiences, some prior observations, and said, I think it's going to look like that. I bet you like 90% that it's going to look like that. But then it took them time to prove it. But they were convinced that this is what's going to be. Okay, so if you want the area of the patch of a surface, that's going to be 12.1, and that's page, God knows. Wait a second, bear with me. It starts at page 951, and it ends at page 957. It's only like 7 pages. Okay, so it's not hard. You have several examples. I'm going to work an example that is straight out of the book, and guess what? You see, that's why I like this problem, because it's in example 1 is exactly the one that I came up with today, and says, find the same tetrahedron thing, find the surface area of the portion of the plane x plus y plus z equals 1, which was that, which lies in the first octant where, what does it mean, first octant? It means that x is positive, y is positive, z is positive, or z. Okay, is this hard? I don't know. Let's find out. So if we were to apply this formula, how would we do that? Is it hard? I don't know. We have to recollect who everybody is from scratch, one at a time.
Just use our K-12 knowledge.
Well, you can do that very well, but let's do it first.
Yeah.
You're sneaking. Let's do it first as Calc 3. And then let's see who comes up with the fastest solution in terms of surface area. By the way, this individual, this whole fat sausage kind of thing is ds. This expression is called the surface element. Make a distinction between dA, which is called area element, in plane. ds is the surface element on the surface. On the surface on top. So practically, guys, you have some hilly part which projects on a domain in plane. The dA is the infinitesimal area of this thingy, and ds is the infinitesimal area of that. What do you mean by that? Okay, imagine this grid of pixels that become smaller and smaller and smaller, okay? Take 1 pixel only and make it infinitesimally small. That's going to be dA, dx dy, dx times dy. What is the corresponding pixel on the round surface? I don't know. It's still going to be given by 2 lines, and 2 lines form a curvilinear domain. And that curvilinear tiny, do you see how small it is? I bet the video cannot see it, but you can see it. So this tiny infinitesimally small element on the surface. This is ds. This is ds. Okay? So if it were between a plane and a tiny square, dx dy, dA, and a ds here, it would be easy between a plane and the floor because you can do some trick like a projection with cosine and stuff. But in general, it's not so easy because you can have a a round patch that's sitting above a domain, and it's just, you have to do integration. You have no other choice. Let's compute it both ways. Let's see, A of S will be integral over domain D. What in the world was the domain D? Domain D was the domain on the floor. And you told me what that is, but I forgot, guys. X is between 0 and 1. Didn't you say so? And Y was between what and what? Can you remind me? Between 0 and 1 minus x. Excellent. So this is the meaning of domain D. And square root of, who is f of xy? Is 1 minus x minus 1. All right, so you guys have to help me compute this animal. F sub x is negative 1. Attention, please. F sub y is negative 1. Okay, so I have to say 1 plus negative 1 squared plus negative 1 squared dA. Gosh, I'm lucky. Look, I mean, I'm not just lucky, but that has to be something beautiful, because otherwise the elementary formula would not be so beautiful. This is root 3, and it rings a bell. Root 3 pulls out of the whole thing, so you have root 3. What is double integral? Okay, let's compute. So first you go dy and dx. X again, you gave it to me, guys, 0 to 1. Y between 0 and 1 minus x. Great. We are almost there. We are almost there. I just need your help a little bit. Square root of 3 goes out. Integral from 0 to 1. What is integral of 1 dy? Is y. Y between 1 minus x on top and 0 on the bottom. That means 1 minus x. If I make a mistake, just shout. Dx. Square root 3 times integral of 1 minus x. X minus x squared over 2. Let me write it separately because I should do that fast, right? Between 0 and 1. What is that? 1/2. That's a piece of cake. This is 1/2. So 1/2 is this thing, and root 3 over 2. And now Alex says, congratulations on your root 3 over 2, but I could have told you that much faster. So the question is, how could Alex have shown us this root 3 over 2 much faster?
Well, that's just a triangle.
It's just a triangle. It's not just a triangle, it's a beautiful triangle. That's an equilateral triangle. And in school, they used to teach more trigonometry, and they don't. And if I had the choice, I'm not involved in the K-12 curriculum standards for any state, but if I had the choice, I would say, teach the kids a little bit more geometry in school, because they don't know anything in terms of geometry. So, there were times in the past, and your parents may know those better, that if somebody gave you an equilateral triangle of a certain side, you would be able to tell them, I know your area. I know the area. I know the area being L squared, square root of 3 over 4. Your parents may know that. Aaron, ask your dad. He will know. But we don't teach that in school anymore. The smart kids do this by themselves. How? Can you show me how? They draw the perpendicular bisector, and there is a theorem actually, but we never prove that in school, that if we draw that perpendicular bisector, then the two triangles are congruent, and as a consequence, well, that is L over 2, L over 2. Okay? So if you draw just the perpendicular, you can prove it using some congruence of triangles. that what you get here is also the median. So it's going to hit right in the middle of the opposite side. So you get L over 2, L over 2. Okay, that's what I wanted to say. And then, with using Pythagorean theorem, you're going to get the height. So the height will be square root of L squared minus L over 2 squared, which is square root of L squared minus L squared over 4, which is square root of 3L squared over 4, which simplified will be L root 3 over 2. L root 3 over 2 is exactly the height. And then the area will be height times the base over 2 for any triangle. So I have the height times the base over 2, which is root 3 L squared over 4. So many people had, when they were young, had to learn it in 7th grade by heart. Now, in our case, it should be piece of cake. Why? Because we know who L is. L is going to be the hypotenuse. We have here a 1 and a 1, a 1 and a 1. So this is going to be the hypotenuse, square root of 2. So if I apply this formula, which is the area of the equilateral triangle, that says root 2 squared, root 3 over 4 equals 2 root 3 over 4 equals root 3 over 2. So can you do that? Are you allowed to do that? Well, we never formulated it actually saying compute the surface of this patch of a plane using the surface integral. We didn't say that. We say compute it, period. We didn't care how. If you can do it by another method, whether to stick to that method, elementary method, or to just check your work and say, is it really square root of 3 over 2? You're allowed to do that. Questions?
So then the length would be square root of 2 squared, which is 2. 2 divided by 4 is the square root of 3 over 2. I'm just
Here,
talking,
yeah,
oh yeah,
you
sorry,
are
I
just
didn't even see you
repeating
plug
what,
it in.
yeah. So the answer I got like this is elementary, and the answer I got like this is with Calc 3. It's the same answer, which gives me the reassurance I wasn't speaking nonsense. I did it in 2 different ways, and I got the same answer. Let's do 1 or 2 more examples of surface integral, surface areas and surface integrals. It's not hard, it's actually quite fun. Some of them are harder than others. Let's see what we can do. Oh yeah, I like this one very much. I remember we gave it several times on the final exams. So let's go ahead and do one like that, because you've seen. Why don't we pick the one I picked before with the eggshells for Easter, like Easter eggs? What was the paraboloid I had on top, the one on top?
8 minus
8 minus x squared minus 1. That's one I'm going to pick. And I'll say, as Easter is coming, the word problem. We want to compute the surface of an egg that is created between, by intersecting the 2 paraboloids, 8 minus x squared minus y squared and x squared plus y squared. So let's. No, that's y, Magdalene. Intersect, make the egg intersect, create the eggshells. Shells, compute the area. And you say, wait a minute, the 2 shells the two eggshells were equal. Yes, I know. I know that the two eggshells were equal, but they don't look equal in my picture. I'll try better. They assume they are parabolas. Assume this was z equals 4. This was 8 minus x squared minus y squared. This was x squared plus y squared. How do we compute, just like Matthew observed, hey, for the volume, I only need half of the egg, multiplied by the 2. The same thing, I'm going to take the one of the two shells, this one, and the surface of the egg will be twice times the surface S1. All I have to compute is S1, right? It shouldn't be a big problem. I mean, what do I need for that S1? I only need the shadow of it and the expression of it. The shadow of it and the shadow of it is this. The shadow of this is this. And the expression, it shouldn't be hard. So I'm gonna start asking you to tell me what to write. What?
Square root of 1 plus.
No, first I'll write the definition. Double integral over d, square root of, as you said, say it again.
1 plus s squared. Square plus s1. Yeah.
All right. So this is the s, and I'm integrating over the domain. Should this be hard? No, it shouldn't be hard. But I'm going to get something a little bit ugly, and it doesn't matter because we will do it with no problem. I'm going to say integral over. Now, the domain D, I know what it is, because the domain D will be given by x squared plus y squared less than equal to 4. So I will know how to deal with that later on. Now what scares me off a little bit, and look what's going to happen. When I compute f sub x and f sub y, those will be really easy. But when I plug everything in here, it's gonna be a little bit hard. Never mind, I'm gonna have to battle the problem with polar coordinates. That's why polar coordinates exist, to help us. So f sub x is minus 2x, right? F sub y is minus 2y. Okay, so what am I going to write over here? Minus 2x squared plus minus 2y squared dA. I don't have much room, but that would mean dx dy. Am I happy with it? No, I'm not happy with it, because here it's going to be like x squared plus y squared between 0 and 4. And I'm not happy with it because it looks like a mess. And I have to find this area integral with a simpler method, something nicer. Now, the question is, does my elementary math help me find the area of the egg? Unfortunately, not. So from this point on is goodbye elementary geometry.
Unless you know the radius.
But they are not spheres or anything. I could approximate the eggs with spheres, but no, I cannot do anything with those paraboloids in
Let's say
K2.
that I know the function of the top.
Yeah, you
And
can.
take put under the integration and find the.
But it's still integration, so can I pretend like I'm a smart 6th grader, and I can, how can I measure that if I'm in 6th grade or 7th grade? with some sort of graphing paper, do some sort of approximation of the area of the egg. It's a school project that's not worth anything though, because I think not in a science fair could I do it.
Unless, in the same radius, I can draw the sphere, and then if I find the distance between the sphere and the axon, the distance between them, and take it off from that. But then
Yeah.
the function actually will look like easier because it will go from y-axis up to the k-axis and then meet each other. So I
Yeah,
took off the area and took off the other area, then I'll find the egg.
yeah. Well, wouldn't that surface of the egg still be an approximation of the actual answer? Anyway, let's come back to the egg.
Yeah, the other way around.
The egg is nest of, no, it's nice, 1 plus 4, x squared plus y squared. Look the beauty of the symmetry of polynomials. X squared plus y squared says I'm a symmetric polynomial and you're my friend because I'm r squared and I know what I'm going to do. So how do we compute, what kind of integral do we need to compute? So S1 will be integral of square root of 1 plus 4r squared. Don't forget the dA contains the Jacobian. So don't write dr, d theta. I had a student who wrote that. That is worth exactly 0 points. So say times r. R between, oh my god, the poor egg, 0 to 2. And theta between 0 to 2 pi. And come on, we've done that in Calc 2. I mean, it's not so hard. So U substitution. U is 4r squared plus 1. That's our only hope. We have no other hope. Du is going to be 8r dr. And r dr is a married couple. They stick together. Where is the purple? The purple is here. R dr is du over 8. This fellow's name is U. He is U. He is not you, but he's like you. Okay. This is okay, so you go 2 pi, because there is no theta. So no theta means, let me write it one more time for you. Integral from 0 to 2 pi, 1 d theta, and he goes out and has fun. This is 2 pi. But then all you have left inside is integral of u. Square root u times 1 over 8 du, close the bracket, where u is between 1 and 17. Isn't that beautiful? That's 17. So you have 2 squared times 416 plus 170. But believe me that from this viewpoint, from this point on, is not very hard. It just looks like the surface of that egg is, whenever it was produced in what factory, in whatever country as a toy factory, they must have done this area testing. So you have 2 pi, 1 over 8 comes out, whether he wants that or not. Integral of square root of u, do you like that? I don't. You have 2/3 u to the 3/2 between down is u equals 1, up is u equals 70. So I was asked, because we've done this in the past reviews for the finals and several finals that present. My students asked me, what do I do in such a case? Nothing. I mean, you do nothing. You just plug it in and leave it as is. So you have, to simplify your life a little bit, what you can do is 2, 2, and 8. What is 2 times 2? 4 divided by 8. So you have pi over 6 overall. Pi over 6 times 17 to the 3/2 and minus 1. One of my students, after he got such an answer, last time we did the review for the final, he said, I don't like it. I want to write this as square root of 17 cubed. You can write it whatever you want. It has to be correct. I don't care how you write it. What if you mess up? Okay, you say, well, this woman is killing me with her algebra over here. Okay, if you understood, suppose that you are taking the final right now. You drew the picture beautifully, you remember the problem, you remember the formula, you write it down. You wrote it down, you got to this point. At this point, you already have 50% of the problem. Yep, and then from this point on, you do the polar coordinates, and you still get like another 25%. You mess it up, you lose some partial credit. But everything you write correctly earns and earns and earns points. Okay? So don't freak out thinking, I'm going to mess up my algebra for sure. If you do, it doesn't matter, because even if this would be a multiple choice, some problems will be show work completely, and some problems may be multiple choice questions. Even if this is gonna be a multiple choice, I will still go over the entire computation for everybody and give partial credit. This is my policy. We are allowed to choose our policies as instructors. So you earn partial credit for everything you write down. Okay, was this hard? It's one of the harder problems in the book. It is similar to example number, like the example 2 in the section. So we did at least 2 examples from the section. And I want to give you one more piece of information that I saw that unfortunately my colleagues don't teach that, and it sort of bothers me. I wish they did. Once upon a time, a long time ago, I taught you a little bit more about the parametrization of a surface. And I want to give you yet another formula, not just this one, but one more. So what if you have a generalized surface that is parametrized, meaning that your surface is not given as explicitly z equals f of x, y. That's the lucky case, okay? That's a graph. We call that a graph, z equals f of x and y, and we call ourselves life. But life is not always so easy. Sometimes all you can get is a parametrization R of u v for a surface. And from that, you have to deal with that. So suppose somebody says, I don't give you f of x, y, although locally every surface looks like a graph, but a surface doesn't have to be a graph in general. Locally, it does look like a graph on a small neighborhood. But in general, it's given by R of u v equals. And that was what? I gave you something like x of u v I plus y of u v j plus z of u v. It's not easy enough like that. Z of u v j, okay. And we said that we have a point. P is R of coordinates u0, v0. And we said we look at that point and we try to draw the partials. What are the partials from a geometric viewpoint? Well, if I want to write the partials, they would be vectors. It's going to be the vector x sub u, y sub u, z sub u, and the vector x sub v, y sub v, z sub v. 2 vectors. Do you remember when I drew them what they were? We said the following. We said, let's assume v would be a constant. So we say v is a constant, and then B equals V0, and then we have P of U0, V0. And then we have another, and we have U equals U0. This guy is going to be who of the two guys? R sub U. When we measure at the point P, R sub U is this guy who is tangent to the line R of U V0. Does it look tangent? I hope it looks tangent. And this guy will be R of U equals U0 means what? U0 and V. So who is free to move? V. So this guy is R sub V. They are both tangents. So do you have a surface? This is the surface. This is the surface. And these two horns, or whatever they are, those are the tangents R sub U, R sub V, the two tangent vectors, the partial velocities. And I told you before, they form the tangent plane. They are partial velocities, they are both tangent to the surface at that point. They form a basis, they are linearly independent. Always, no, but we assume that R sub U and R sub V are non-zero, and they are not collinear. How do I write that? They are not parallel. So guys, what does it mean? It means, we talked about this before, the velocities cannot be zero. And R sub U, R sub V cannot be parallel, because if they are parallel, there is no area element. There is no tangent plane between them. What they form is the area element. So what do you think the area element will look like? It's a magic thing. The surface element actually will be exactly the area between RU and RV times du dv. Say it again, Magdalena. What the heck is the area between the vectors R sub U, R sub V? You know it better than me, because you're younger and your memory is better, and you just covered this in chapter 9. When you have a vector A and a vector B that are not collinear, what was the area of the parallelogram that they form? Magnitude of the cross product. Excellent. This is exactly what I was hoping for. The magnitude of the cross product is the area element. So you have ds, infinitesimal element, surface area, surface element, will be exactly the magnitude of the cross product of the two velocity vectors, du dv. Du dv can also be written dA in this case, because it's a flat area on the floor. It's the area of a tiny square on the floor, infinitesimally small square. So remember that. And you say, wait, Magdalena, you are just feeding us formula after formula, but we don't even know. Okay, this makes sense. This looks like I have some sort of tiny parallelogram, and I approximate the actual curvilinear patch. I'm going to draw it on my hand. So this is, oh my God, my son will make fun of me. So this curvilinear patch between two curves on my hand will be actually approximated by this, what is this rectangle? No, it's a parallelogram. Thank you so much. So this is an approximation again. Okay, so this is the area of the parallelogram. And that's what we define as being the surface element. It has to do with the tangent plane. But now you're asking, but shouldn't this be the same as the formula root of 1 plus f sub x squared plus f sub y squared dx dy? Yes, let's prove it. Let's finally prove it, that the meaning of this area will provide you with the surface element in terms of x and y, just the way you did not prove it, You discovered it, remember guys? You came up with a formula as a conjecture. You said if we generalize the arc length, it should look like that. You sort of smelled it. You said, I think, I feel, I'm almost sure, but did you prove it? No. So starting from the idea of the area element that I gave before, do you remember that we also had that signed area between the dx and dy, and we used the area of the parallelogram before? We also allowed it to go oriented, plus minus. Okay? All right, so this makes more sense than what you gave me. Can I prove what you gave me based on this and show it's one and the same thing? So hopefully, yes. If I have my explicit form z equals f of x and y, I should be able to parameterize this surface. How do I parameterize the surface in the simplest possible way? X is u, y is v, z is f of uv. And that's it. That means r of uv as a vector will be angular bracket uv f of uv. Now you have to help me compute r sub u and r sub v. They have to be these blue vectors, the partial velocities, r sub u, r sub v. Is it hard? Come on, it shouldn't be hard. I need to change colors. So can you tell me what they are? What's the first one? Good. What's next? 0. Thank you. F sub u. Very good. F sub u or f sub x is the same because x and u are the same. So let me rewrite it 1, 0, f sub x. Now, the next guy. 0, 1, f sub v, which is a 0, 1, f sub y. 0, 1, f sub y. Now I need to cross them. I need to cross them and I'm too lazy because it's 2:20, but I'll do it, I promise. So with your help and everything, I'm gonna get to where I need to get. You can start. I mean, don't wait for me. Just do it yourselves and see what you get and how hard do you think it is to compute the thing. I will do the norm at the magnitude later. R sub u, R sub v is cross product will be ijk. One, 0, f sub x, 0, 1, f sub y. Is this hard? It shouldn't be hard. So, I have minus f sub x, what? I'm sorry, I for an I, okay. J, again minus because I need to change. When I expand along the row, I have plus, minus, alternating. So I need to have minus, the determinant is f sub y, times j, plus k times this fellow. But that fellow is 1, is the minor 1, for God's sake. So this is so easy. I got the vector, but I need the norm. But so what? Look how I'm there, guys. I'm really there. It's a piece of cake. I take the components, I squeeze them a little bit. No, I square them, and I sum them up, and I get square root of 1 plus, exactly, 1 plus f sub x squared plus f sub y squared. This is u and v. And this is dx dy, which is dx dy, which is dA. This is the tiny floor square of an infinitesimal square on the floor. Okay? And what is this again? This is the area of a tiny curvilinear patch on the surface that's projected on that tiny square on the floor. All right? Okay. So, now you know why you get what you get. One last problem because time is up. No, I'm not. I'm just kidding. We still have plenty of time. This is a beautiful, beautiful problem, but I don't want to finish it. I want to give you the problem at home. It's like the one in the book, but I don't want to give you exactly the one in the book. I want to cover something special tonight. We are all familiar with the notion of spiral staircase. But spiral staircases are everywhere in elegant buildings, official buildings, palaces, theaters, houses of multimillionaires in California. And even people who are not millionaires have some spiral staircases in their houses, maybe made of wood or even marble. Did you ever wonder why these spiral staircases were invented? If you go to most of the castles on the Loire Valley, or many European castles have spiral staircases, many mosques, many churches have these spiral staircases. I think it was about a few thousand years ago that was documented for the first time that the spiral staircases consume the least amount of materials to build. Also, what's good about them is that they, for confined spaces, like you have something like a cylinder tower like that, that's the only shape you can build that minimizes the area of the staircase. Because if you start building a staircase like ours here, it's not efficient at all, in terms of construction, in terms of material and service. So you better struggle at drawing, at actually making these stairs that are not even, they're not even even. Each of them will have like a triangle or what is this? Not a triangle, but more like a trapezoid, and keeps going like that. This comes from a helix, obviously, and we have to understand why this happens. And I will introduce the surface called helicoid. And the helicoid will have the following parametrization. By definition, u cosine v, u sine v, and v. Assume u is between 0 and 1, and assume v is between 0 and 2 pi. Draw the surface. Also, find the surface area of the patch u between 0 and 1, v between 0 and pi over 2. So I go, I'm in trouble. Now, how in the world am I going to do this problem? It looks horrible, and it looks hard, and it even looks hard to draw. It's not that hard. It's not that hard at all, because you have to think of these extreme points, the limit points of u and v, and see what they really represent for you. Put your imagination to work and say, this is the frame I'm starting with. This is the x and y and z frame with origin 0. And I better draw this helicoid because it shouldn't be hard. So for u equals 0, what do I have?
Oh, it's real.
I don't know, it looks weird, but Alex said it. 0, 0, v. V is in my parameter in real line, so I have the whole z-axis. So one edge is going to be the z-axis itself. Does it have to be only positive one? No, who says so? My problem says so. That v only takes values between 0 and 2 pi. Unfortunately, I'm limiting v between 0 and 2 pi. But in general, v could be any real number. So I'll take it from 0 to 2 pi, and this is going to be what I'm thinking of. One edge of the staircase. Okay? Is the interior edge the axis? Let's see what happens when u equals 1. That's another curve of the surface. Let's see what I get. Cosine v, sine v, and v. And it looks like a friend of yours, and you have to tell me who this is. If v were bt, what is sine, cosine t, sine t, t?
Sphere.
It's your
Helix.
helix that you loved in chapter 10 and you made friends with, and it was a curve that had constant curvature and constant torsion, and it had constant speed. And the speed of this, for example, would be square root of 2. If you have the curiosity to compute it, it will have speed square root of 2. Can I draw it? I better draw it, but I don't know how. So I have to think of drawing this for v between 0 and 2 pi. When I'm at 0, when I have time v equals 0, I have the point 1, 0, and 0. And where am I? Here. 1, 0, 0. And from here, I start moving on the helix and going up. And see, my hand should be on, well, this is the stairs. It's obviously a smooth surface. This is a smooth surface, but the stairs that I was talking about are this discretization of the smooth surface. I have a step, another step, another step, another step. So it's like a smooth helicoid, but discretized as step functions. Forget about the step functions. Assume that instead of the staircase in the church, you don't want to go to church, you want to go to water park. You want to go to Six Flags. You want to go to whatever, Disney World, San Antonio, something. This is a slide. You let yourself go. This is you going down, swimming, I don't know, upside down. I don't know, this is you going down. So this is a smooth slide in a water park. That's how you should imagine. And it keeps going. If I start here, again, look, this is what I'm describing. A helicoid, my arm moved on this. Again, I draw the same motion. My elbow should not do something crazy. It should keep moving on the z-axis. And I perform the pi over 2 motion when the stair, I don't know how to call it, this line becomes horizontal. When v equals pi over 2. So for v equals pi over 2, I move from here straight to here.
Doesn't it go around?
It goes around. But see what I asked? I only asked for the patch.
Oh, for pi.
First of all, I said it goes around, so I'll try to go around, but it's hard. Oh, wish me luck. 1, 2, 3. I cannot go higher.
So if
It
was-
goes to pi.
If it went to 2 pi, it would actually wrap completely
It
around.
will wrap
and
one
like
time.
right above where it started.
Exactly. So if I started here, I end up parallel to that up. But it's 2 pi is too high for me, right? So I should go slower maybe. I'm up after 2 pi, in the same position.
This is pi over 2, just kind of like.
When I'm pi over 2, I just perform from here to here.
So that's why it's asking for the
And it's asking for what area does my arm from here to here sweep at this point, from this point to this point. It's a smooth surface, so it's generated by my motion and stop. It's a ruled surface. It's a ruled catchable surface. Somebody tell me how I'm going to do this, because this is not with square root of 1 plus f sub x squared plus f sub y squared. That is for normal people. You are not normal people. They never teach this in honors. In honors, we don't cover this formula, but you are honors. So, do I want you to finish it at home with a calculator? All I want is you to be able to set up the integral, and I think knowing you better and working with you, I think you have the potential to do that without my help, with all the elements I gave you until now. So the area of S will be the blue slide. These are all, when you slide down along helices. You and your friends, you can go down along helices. Okay, so that's what you have. Will double integral over a certain domain D. Which is that domain D? That domain D is u between 0 and 1, and v between 0 and pi over 2, because that's what I said I want here. Of what? Of magnitude of r sub u times r sub v cross product du dv. You need to help me though, because I don't know what I'm going to do. So, who starts? R sub u is? I'm not doing anything without you, I swear. Okay? Cosine v. Sine v. 0. R sub v equals?
Negative u sine v.
Very good. U cosine v. And 1. And this goes on my nerves. But why can I do nothing? Okay? All right. So, I have to compute the what? The cross product. IJK, of course, right? IJK cosine v sine v 0 minus u sine, oh my God, where was it? It's there, you gave it to me. U cosine v and 1 minus u sine v, u cosine v and 1. Okay. I times that. Sine vi. Sine vi. J has a friend. Is this minor cosine v times 1, but I have to change the sign. Are you guys with me? It's really serious that I have to think of changing the sign. Minus cosine v times j. Are you with me? This times that with the sign change. And then plus, what is, well, this is not so obvious, but you have so much practice and make me proud. What is the minor that multiplies k? This red fellow. You need to compute it and simplify it so I don't talk too much. You, excellent. How did you do it, Nitish?
Sine squared equals cos squared.
So you group together cosine squared plus sine squared minus minus is a plus. And you said u. It's u. Good. Plus u times k. Good. It doesn't look so bad. Now that you look at it, it doesn't look so bad. You have to set up the integral, and that's going to be what? Square root of this fellow squared plus that fellow squared plus this fellow squared. Let's take our time. You take these three fellows, square them, add them up, and put them under square root. Is it hard?
1 plus u squared.
1 plus u squared. Now, the thing is, I don't have a Jacobian. This is du dv. The Jacobian is 1. So this is what I have. Now, between the endpoints, I have to think. V has to be between 0 and pi over 2. And u has to be between 0 and 1. Do you notice anything? That's exactly what I wanted to tell you. V is not inside. V says I'm independent. Please leave me alone. I'll go up, take a break. Pi over 2. But then you have integral from 0 to 1 square root of 1 plus u squared du. I want to say a remark. Happy or not happy, shall I be? Here you need either the calculator, which is the simplest way to do, just compute this simple integral from 0 to 1 square root 1 plus u squared du. Or what do you have in this book that can still help you if you don't have a calculator? A table of integration. Integration table. Please compute this. I mean, you cannot give me an exact value, but give me an approximate value by Thursday. Is today Tuesday? Yes, by Thursday. So please let me know how much you got from your calculator or from integration table. So we have this result. And then I would like to interpret this result geometrically. What we can say about the helicoid that I didn't tell you, but I'm going to tell you just to finish. Have you been to the Omnimax Science Spectrum, the one in Lubbock, or any other? I think there are everywhere, right? I mean, everywhere. We are a large city. Only in the big cities can you go to a science spectrum museum, kind of like that. Have you played with the soap films? Okay. Do you remember what kind of wireframes they had? They had a big tub with soapy water, with soap solution, and then there were all sorts of they had a wire with thick rods that looked like a prism. They had the cube that they wanted you to dip into the soap tub. They had and there comes the beautiful thing. They had this. A spring that they took from your grandfather's bed. No, I don't think it was flexible at all. It was a helix made with a rod inside. A metal rod inside and attached to the frame of that. There was the metal rod and this helix made of hard iron, and they were sticking together. Have you dipped this into the soap solution? And what did you get? That's exactly what you get. You can get several surfaces. You can even get the one on the outside that's unstable. It broke in my case. It's almost like a cylinder. Okay? The one that was pretty stable was your helicoid. The helicoid is a so-called soap film. Soap film or minimal surface. Minimal surface. So what is a minimal surface? A minimal surface is a soap film. A minimal surface is a surface that tends to minimize the area enclosed in a certain frame. You take a wire that looks like a loop. It's all skew curve. You dip that into soap solution, you pull it out, you get a soap film. That's a minimal surface. Okay? So all the things that you created by taking wires and dipping them into the soap tub and pulling them out, they are not just called soap films, they are called minimal surfaces. Somewhere on the wall of the science spectrum they wrote that. they didn't write much about the theory of minimal surface, but there are people, there are famous mathematicians who all their life studied just minimal surfaces, just soap films. They came up with the results. Some of them got very prestigious awards for that kind of theory for minimal surfaces. And these have been known since approximately the middle of the 19th century. There were several mathematicians who discovered the most important minimal surfaces. There are several that you may be familiar with them and several of you may not be familiar with them. But another one that you may have known is the catenoid. And that's the last thing I'm going to talk about today. Have you heard of a catenary? Have you ever been to St. Louis? St. Louis, the city, St. Louis, with the arch. Okay, did you go to the arch? No? You should go to the arch. It looks like that. It has a big base. So it looks so beautiful. It's thicker at the base. This was based on a mathematical equation. The mathematical equation it was built based on was cosh x. What is cosh as a function? Now I'm testing you, but I'm not judging you. Okay, if you forgot, e to the x plus e to the negative x over 3. If it's minus, it's called sinh.
Yep.
So the one with plus. You can have x over a and you can have 1 over a in front. It's still called a catenary. Now, what this is a catenary. The shape of the arch of St. Louis is a catenary. But you are more used to the catenary upside down, which is any necklace. Do you have a necklace? If you take any necklace, that is, it has to be homogeneous, not one of those like you have a pearl hanging or you have several beads and no. It has to be a homogeneous metal, think gold, solid gold, but that kind of liquid gold. Do you know what I'm talking about? Those beautiful bracelets or necklaces that are fluid and you cannot even see the different links. So you hang it at the same distance, at the same height. What you get, Galileo proved was not a parabola because people at that time were really stupid. So they thought, hang a chain from a woman's neck or some sort of beautiful jewelry, that must be a parabola because it looks like a parabola. And Galileo Galilei says, these guys are nuts. They don't know any mathematics, any physics, any astronomy. So he proved in no time that the chain cannot be a parabola. And he actually came up with that. If A is 1, you just have the cosh x. So this is the chain. If you take the chain, that's a chain upside down. The one is in here. You take a chain, let's say y equals cosh x, to make it easier. And revolve that chain, you get a surface of revolution. And this surface of revolution is called catenoid. Okay. How can you get the catenoid as a minimal surface, expressed as a minimal surface? There are people who can do that. They have the ability to do that. And they try to have an experimental thing at the science spectrum as well. And they did a beautiful job. I was there. So they took two circles made of plastic. You can have them circles made of wood, made of iron or steel or anything. But they have to be equal circles. And you touch them and you dip them both at the same time into the soap solution. And then you pull it out, but very gently because you have to be very smart and be like a surgeon. If your hands start shaking, it's goodbye minimal surfaces because they break, they collapse. So you have to pull those circles with the same force, gently one away from the other. What you're going to get is going to be a film that looks exactly like that. These are the circles. If after a certain distance of moving them apart, the soap film will collapse and will burst. There's no more surface inside. But up to that moment, you have a catenoid. And this catenoid is a minimal surface. It's trying to, for the frame you gave it, which is the wire frame, minimize the area. It's not going to be a cylinder. It's way too much area. It's going to be something smaller than that. So something that says, I'm an elastic surface. I'm occupying as little area as I can. Because I live in a world of scarcity. And I try to occupy as little as I can. So it's based on a principle of physics. The surface tension of the soap films will create this minimization of the area. So all you need to do is remember, you know the helicoid and catenoid only because you're honor students, so thank the Honors College for giving you this opportunity. All right? I'm not kidding. It may sound like a joke, but it's half joke, half true. You learn a little bit more interesting stuff than other people. Enjoy your week. Good luck with homework. Contact me about any kind of homework you couldn't solve. Actually, my advisor, she is the one who does the paper. But I can take her this far so you can start the paperwork. I think you would be a very like major, not just mathematics. If you don't get at least a math minor, you're going to get beta. So that is for my yes, and so that's it. I'll take you there now. Okay. Second floor, you have to go behind. This is the main office. Yeah, you have to go all the way behind. Okay.
Already finished it. Next week we need help.
Because I don't want to give you anything new. I don't want to get you in any kind of trouble. But the problems that I solve on the board are the primary thing. I would say 60% of what you see on the midterm is something that we cover in class. And the rest, 40%, will be something not too hard, but something standard out of your web work, homework, the one that you saw. It shouldn't be hard. You're welcome.
We're trying to join the Honor Society, but we can't make that thing tomorrow. Can we still join?
You can still join. Remind me to give you the golden pin, the brochures, all the information, and then when you get those, you'll give me the $34.
Okay.
It's
All right.
a lifetime thing.
Awesome. Thank you. Okay.
You're welcome. Both of you want to?
Yeah,
And you cannot come tomorrow?
Yeah, I might not.
I wanted to bring something, eat some snacks, but I don't know how that. I need to count, see how many people can come, and it's gonna be in my office. All right.
Tish, were you in the tennis tournament?
Yeah,
You the guy who won?
yeah,
Congratulations. I was like, it's like, I know that name.
okay.
I know.
You won?
He's in my
Yeah.
job.
You won it!
Yeah.
The tennis tournament?
Yeah, that was honor tennis tournament.
Congratulations.
Yeah.
Why don't you blab a little bit about yourself? You're so modest. You're not
It's all right.
It's all right. It's not a big deal.
Were people good? Yeah.
All
I
right.
have 9 strict